So the things we were talking about before, we talked about non-electrolytes, right? Strong electrolytes are going to affect the freezing point and the boiling point more strongly because they break into ions. For a given number of moles, you're going to get more particles. Well, it turns out that you can't exactly predict what they're going to do. Like for sodium chloride, we would expect that if we have 1 mole of sodium chloride, we would have 1 mole of chloride ions, and 1 mole of sodium ions. But actually, it doesn't quite work as simply as that. And so we have this Vant factor, which is abbreviated with a lowercase I. This is the ratio of moles of particles in the solution divided by the moles of formula units dissolved. And it doesn't always come out to be exactly what we think it should be because some of the ions pair up in solution. And so here's what that looks like. So here we have solvated chloride ion and solvated sodium ion, but they're like, hey, let's go around together. And so they're not really separate. And so the Vant factors are experimental correction factors. So for a non-electrolyte, we would expect a Vant factor of 1, and the measured factor is also 1. The number of moles of particles is equal to the number of moles of molecules that you put in there, because nothing breaks apart. For sodium chloride, we would expect a factor of 2. It's actually 1.9. Magnesium sulfate, we expect 2 as well, because we have 1 magnesium ion, 1 sulfate ion in 1 formula unit. It's actually 1.3. So they're all slightly smaller than what we would expect. So how do we use these? Well, we just throw it in to each of these colligative property equations we've been looking at. So here, I comes in times the molality, and it just gets thrown in there to each of them. These are for strong electrolytes. And the I is something you just look up in the table, or they give it to you. Calculate the freezing point of an aqueous 0.10 molal iron chloride solution using a Vant factor of 3.2. Well, we need the freezing point depression constant for water, which I think was 1.86 degrees Celsius per molal. And so this is a strong electrolyte solution, so it's going to be I m times Kf. They gave us I, it was 3.2. They gave us the molality, 0.10 molal. And the freezing point depression is for the solvent, which is water, 1.86 degrees Celsius per molal. 3.2 times 0.1 times 1.86. So the freezing point depression is 0.5952 degrees Celsius, 2 sig figs on that. So what's the freezing point? We'll take the actual freezing point minus the change. And so we end up with minus 0.5, it's 0.60 degrees Celsius. Any questions? So the Vant factor, it's a correction factor, and you just multiply it in there. Strong electrolytes also have a larger effect on the vapor pressure lowering, as we would expect. And so you would also have to account for the dissociation of the solute when you're calculating the mole fraction of the solute. A solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. These are the sorts of, if this was an exam question, this would be one where I'd probably find a number of just blank. People look at that and like, bleh, don't want to do that. We're going to do it. So what do we know? We've got the vapor pressure of pure water. We've got the vapor pressure of the solution. So there was an equation for that, right? The vapor pressure equaled the mole fraction times the normal or standard vapor pressure. So that means that we could find out what the mole fraction of water is, right? So, because it was the mole fraction of the solvent. So the mole fraction of water is going to equal the vapor pressure of the solution divided by the vapor pressure of pure water. So 25.7 torr divided by 31.8 torr. So the mole fraction of water is 0.80818. No units on that. It's a mole fraction. That means there's 0.80818 moles of water per 1 mole of solution. Right? Yeah. This mole fraction is the moles of the thing you're looking at divided by the moles of the whole solution. So 0.80818 moles of water per 1 mole solution. Well, what's in the solution? Well, we have 0.115 moles of water. That looks like that might be a useful conversion factor, huh? We could take moles of water and find the moles of solution. So moles of solution over 0.80818 moles of water. That's not what I wanted to do. That is what I wanted to do. The units cancel out. We get moles of solution. 0.115 divided by 0.80818 equals 0.142295. I'm losing my sig face here, but it's that 8, this 8, and there's 3. So there's 3 on that one. That's moles of solution. And then, we've been caught up in calculating, and we're like, oh, wait a minute, what are we trying to calculate again? Moles of sodium chloride. What's wrong with that number? The moles no. Never mind. I was having a brain fart. I was seeing 0.15 moles of water and 0.14 moles of solution and thinking, no, wait, that's impossible. Never mind. Never mind. So if this is the whole thing, and this is the part, how much is the other part? Subtract, right? So this is the moles of solution. See if I can copy it down right. Moles of solution. And if we subtract the moles of water, then we'll get the moles of sodium chloride. 0.02? 295? Okay, so we're subtracting, and we need 3 decimal places, so it'll be right there. 0.027 moles of sodium chloride. Any questions? These are challenging problems because the problem is most likely going to be something that you haven't exactly seen before. And so then you have to think about it and figure it out. And that can be challenging sometimes, especially if you're exhausted and stressed out, which is not a good situation for an exam, but a common one. Colligative properties in medical solutions. Osmotic pressure is really, really important when solutions are administered as IV fluids. What they do is they typically talk about a solution, they talk about the osmotic pressure relative to whatever situation they're dealing with. Could be compared to blood, right? So the osmotic pressure. You want the osmotic pressure to be the same of the solution that you're putting into someone's blood. You want it to be the same as the blood. Because if you put in a solution that is isoosmotic or isotonic is the word I've heard more often, then the blood cells which are surrounded by semi-permeable membranes, will retain their normal shapes and everything's good. If you put in something that's hyperosmotic, it's going to pull water out. It's got a higher osmotic pressure. And so the water is going to come out of the red blood cells, causing them to shrivel up. And that's not good. If you put in hypoosmotic solution, like if you were to inject pure water into someone's veins, that's not good because the water's going to flow into the blood cells, the red blood cells. They're going to swell, and if it keeps going on, they're going to burst. That's not good either, right? So really important, that's why they're always giving you these saline solutions. Why are they pumping all this salt into me? Well, it's 0.9% saline, and that's so that the solution is isoosmotic with your blood and doesn't cause a net flow of water into or out of your cells. It just goes along and takes whatever they're trying to give you with it. Yeah, I kind of said that. So, yeah, 0.9% or 0.9 grams per 100 milliliters. So in medicine, they often express concentrations is mass percent to mass volume percent, mass of solute per volume of solution. Because if you're putting a solid into the solution, it's easy to weigh it, and then the volume of the solution is the easiest thing to measure.